Hi, I'm Jeff Groh, and this is Differential Equations, Lecture 7. Today we're going to talk about the non-homogeneous case. In particular, we're going to look at equations of the form a double prime y double prime plus by prime plus cy equals f of x, where we're going to assume that f of x is not identically zero. To begin with, we need to analyze some theory underlying our solution process. The theory is based upon the following theorem. If y1 and y2 solve a linear differential equation, then their difference solves the corresponding homogeneous equation. The proof of the theorem follows in a natural way. We plug the difference y1 minus y2 into the differential equation and just see what happens. We can rearrange the terms. The derivative of the difference is the difference of the derivatives. So we can rewrite this first as a(n) of x, the nth derivative of 1 minus the nth derivative of y2 and then using the commutative and associative properties of addition in addition to the distributive law, we can rewrite the sum separating out the y1s and the y2s minus what you get when you plug y2 in of x. Each of these solves the non-homogeneous equation, which means that each of them results in f of x. And so you get f of x minus f of x, and that equals 0 for all x. That is the end of the proof. This gives us a simple procedure for solving non-homogeneous problems. If yp is, and this is subscript p for particular, we call this the particular solution. If yp is any solution to one of these nth order linear non-homogeneous problems, and y hat is any other solution, then yp, the difference between the two, is a homogeneous solution. Y sub h, the homogeneous solution, where y sub h is a solution to the corresponding homogeneous equation. We know how to find a complete solution to homogeneous equations. So when we find the solution to the homogeneous equation, if we add that to any particular solution, then we can construct any other solution to the differential equation. We'll state these results as a theorem. The general solution to one of these nth order linear problems that is non-homogeneous is given by particular solution plus homogeneous solution, where yp is any solution to, we'll call this equation star, and yh is the general solution to the corresponding homogeneous equation. We are going to have two distinct methods for solving these non-homogeneous problems. First, there's the method of undetermined coefficients. Second, a method called variation of parameters. Undetermined coefficients might better be described as the method of guessing. I teach this by example. It requires that you learn how to make good guesses. The problem being that it's conceivable that you may never make a good guess. This method is said to be non-deterministic. Non-deterministic means that you may never end up with the right solution. This is the reason why fourth graders sometimes have problems with long division. They're unwilling to make an incorrect guess for whatever reason. And so they fail. You need to make a guess. If that guess is good, go for it. If it's not, make a better guess. I'm going to teach you how to make good guesses by way of example. Consider the differential equation y double prime plus 5y prime plus 6y equals e to the x. Step 1. Step 1 will solve the corresponding homogeneous equation. This is absolutely necessary. Anyway, the characteristic equation is lambda squared plus 5 lambda plus 6 equals 0. Factoring the left-hand side, factors of 6 are 2 and 3, which happen to add up to 5, so this is the factorization. We get lambda equals -2 and -3. This implies then that the homogeneous solution is C1 e to the -2x plus C2 e to the -3x. We'll put that in a bucket. In step 2, we make a guess. If y and its derivatives can be combined through some linear combination to yield e to the x, what do you suppose that a particular solution will have the form a e to the x? It is the constant a that is the undetermined coefficient in this case. Notice that for this particular problem, yp prime and yp double prime are also equal to a e to the x. When we substitute these into the differential equation, we get a e to the x plus 5a e to the x plus 6a e to the x equals e to the x. On the left-hand side, the terms combine to make 12a e to the x, and that equals e to the x. We can divide both sides by e to the x and solve to obtain a is 1/12. That means that the particular solution is 1/12 e to the x. It follows from these facts that the general solution will be the particular solution plus the general homogeneous solution. On this next example, I'd like to make only one change, and that is that the forcing function is 2x instead of e to the x. We already know the result from step 1, that the homogeneous solution is c1 e to the negative 2x plus c2 e to the negative 3x. So there's no point in going through that again. What changes is step 2. We need to make an appropriate guess. When I'm in class, I ask my students to make that guess for me, and almost always they give me the following guess for a particular solution. As you will see, this is a bad guess. We'll show why. Note that if I assume that the particular solution is a constant times x, the derivative is a, and then the second derivative is 0. Plugging these into the differential equation, we get 5a plus 6ax equals 2x. This represents a polynomial equal to a polynomial. The only way a polynomial can equal another polynomial is if corresponding coefficients are equal. In this case, the coefficient of x on the right is 2. The coefficient on the left is 6a. So we get 6a equals 2. But we also must have, at the same time, 5a, the constant on the left, equal to 0, the constant on the right. This gives a is 1/3. This gives a is 0. This represents a contradiction. This is the mathematical symbol for a contradiction. It's two arrows colliding. You can't have both a is 1/3 and a is 0, which implies then that there does not exist a solution of this form. You needed to see how it is that guesses crash and burn. They yield contradictions. Once you've decided that your solution guess was no good, you have to go back and make a better guess. In this case, a better guess might be ax plus b. Add a constant. We were off by a constant after all in that last example. In this case, yp prime is a and yp double prime is 0. Plugging these into the differential equation, we get 5a plus 6 ax plus b equals 2x. You can see now that the coefficient of x on the left will be 6a and the coefficient on the right will be 2. So we get 6a equals 2, or a is 1/3. However, the constant term on the left yields 5a plus 6b. That must equal the constant term on the right, which is 0. Plugging in a equals 1/3 here, we get 5/3 plus 6b equals 0. We move the 5/3 to the right and divide by 6. This yields b is minus 5/18. That gives a particular solution of the form 1/3 x minus 5/18. You can see that the guess that we made this time left just enough flexibility for us to end up with two equations and two unknowns that allowed us to solve for each. We can now write down the general solution. It's 1/3 x minus 5/18 plus c1 e to the negative 2x plus c2 e to the minus 3x. In our next example, we're not going to change much, just the forcing function on the right-hand side again, so that we don't have to find a new homogeneous solution. What we're going to do is put sine of x over on the right-hand side as our forcing function. Once again, the homogeneous solution is c1 e to the negative 2x plus c2 e to the negative 3x. The only question is, what is a good guess for the particular solution? Again, I ask my students this question, what is a good guess? And they often tell me that a good guess is a constant times sine of x. As you'll see, this also is a bad guess. If we make this guess a sine of x, then the particular solution has derivative a cosine of x and second derivative minus a sine of x. You might already detect what the problem might be. When we plug these into the original differential equation, we're going to get a cosine on the left, and there are no cosines on the right to cancel that with. Let's go ahead and plug it in anyway. We get minus a, can I use capital S for sine and capital C for cosine, plus 5a cosine plus 6a sine equals sine. Now, once again, because sine and cosine are linearly independent functions, we equate corresponding coefficients on the left and on the right. In this case, we get a coefficient of 5a for the sine on the left. That has to equal the coefficient of sine on the right, which is 1. But the coefficient of cosine on the left, 5a, must equal the coefficient of cosine on the right, which is 0. In this case, we get a is 1/5, but also a is 0, and that is a contradiction. Therefore, that is a bad guess. To make a better guess, we reflect on the problem with the previous guess. In the previous guess, we had sine involved, and we ended up with a cosine. Maybe we need both sine and cosine in our guess. And so that's the assumption we make. A sine of x plus b cosine of x. We'll calculate the derivatives. A cosine minus b sine, and yp double prime is minus a sine minus b cosine. Plugging all of this into the differential equation, we get minus a sine minus b cosine plus 5 times a cosine minus b sine plus 6 times a sine plus b cosine equals sine. To solve this equation, we need to collect coefficients of sine and coefficients of cosine separately. So what are the coefficients of sine? Well, we'll have a 6a sine and a negative a sine. So that's a 5a times our sine function here. But we also get a minus 5b sine. Now for the coefficients of cosine. We'll have here a negative b cosine and a positive 6b cosine, yielding 5b cosine. And then we get plus 5a cosine equating coefficients on each side of the equation, we get 5a minus 5b equals 1. The coefficient of sine on this side is the coefficient of sine on this side. And also, 5a plus 5b equals 0. The coefficient of cosine on this side is the coefficient of cosine on the right-hand side. Dividing through by 5, we see that b is minus a, which we can substitute into the previous equation. Making the substitution, we have 5a plus. If b is replaced by negative a, we'll get another 5a equals 1, and hence a is 1/10. That implies that b is negative 1/10. It follows then that our particular solution is 1/10 sine of x minus 1/10 cosine of x, and then the general solution is the particular solution, 1/10 sine of x minus 1/10 cosine of x plus c1 e to the negative 2x plus c2 e to the negative 3x. Another issue to consider is what happens if you have two terms in the forcing function, and it may be easier to solve for the particular solution to each of those individually. Is that even possible? Let's consider an important theorem that involves two principles of superposition. Here's the theorem. It is the two superposition principles. First, if y1 through yk solve an nth order linear homogeneous problem, then any linear combination of those is also a solution. We've taken advantage of this fact already when constructing the general homogeneous solution. To superimpose two waves is to add them one on top of another. The second form of the superposition principle is that if y1 solves one of these nth order linear non-homogeneous problems, we don't need the subscript here, it's just the equation that y1 solves. With a forcing function f1, y2 solves the similar equation with a forcing function f2, etc. Let's suppose yk solves the same equation, but with forcing function fk. Then, if you add these functions together, not as an arbitrary linear combination, but one where the coefficients are 1, this solves the equation with forcing function equal to the sum of the forcing functions. This tells us how to solve that problem we just had up. We'll find the particular solution for each of the individual forcing functions and add them together. Back to our example. It follows immediately from the previous examples that the general solution is 1/3 x minus 5/18 plus 1/10 sine of x minus 1/10 cosine of x plus c1 e to the negative 2x plus c2 e to the minus 3x. Before moving on, I'd like to show you one more thing that can go wrong with your guesses. Consider the differential equation y double prime plus 2y prime plus y equals e to the negative x. It seems like a simple little problem. In step 1, we solve the corresponding homogeneous equation, so we write down the characteristic equation, and we get lambda plus 1 quantity squared equals 0. We get a solution, lambda equals minus 1, which has multiplicity 2, and that means that the homogeneous solution is c1 e to the negative x plus c2x e to the negative x. In step 2, we have to make a guess. Now, since the forcing function involves e to the negative x, you might guess that a e to the negative x would be a reasonable choice, but it's not. The reason it's not is that anything of this form is already in the homogeneous solution set, which means that if you plug this into the left-hand side in the differential equation, you will get 0, not e to the negative x. So this is wrong. Can you think of a way of finding something that involves e to the negative x that is linearly independent of e to the negative x? If you suggested that you write x e to the negative x, you're on the right track, but you're still off. And the reason you're off is that that's part of this second term in the homogeneous equation. If you plug this into the differential equation again, you will get 0, not e to the negative x. So multiplying by x doesn't work, and leaving it as just e to the negative x doesn't work. You need something linearly independent from those two. What's a reasonable choice? How about a times x squared e to the negative x? Let's multiply by one more factor of x to generate something linearly independent. Let's see how that works out. If we make a guess, ax squared e to the negative x, what is yp prime? We need to use the product rule. So we have 2ax e to the minus x minus ax squared e to the minus x. For the second derivative, we need to calculate using the product rule twice. That gives us 2a e to the minus x minus 2a x e to the minus x. That gives me the product rule applied to the first term. When we apply this to the first factor on the second term, we get another 2ax, yielding 4ax e to the minus x. And then when we take the derivative of the e to the minus x, we'll get plus ax squared e to the minus x. Plugging all of this into the differential equation, we have 2a e to the minus x minus 4ax e to the minus x plus ax squared e to the minus x plus twice 2ax e to the minus x minus ax squared e to the minus x plus ax squared e to the minus x equals e to the minus x. Now we need to combine like terms on the left-hand side. In this grouping we have an ax squared e to the negative x, and here's another ax squared e to the negative x. 1 plus 1 is 2 ax squared e to the negative x. When we distribute the 2 here, we'll get a minus 2 ax squared e to the negative x. So this term, and this term all cancel out. Then, here we have negative 4ax e to the negative x and positive 4ax e to the negative x. So this term and this term cancel out. We're left with only this one term, 2a e to the negative x. Equating coefficients on each side, we deduce that 2a equals 1, and hence a is 1/2. This gives us the particular solution 1/2 x squared e to the negative x. It follows then that the general solution is 1/2 x squared e to the minus x plus c1 e to the minus x plus c2 x e to the minus x. We're ready now for a second method called variation of parameters. As we saw, the method of undetermined coefficients, or the method of guessing, is non-deterministic, meaning you have to make a guess and there's no guarantee that you'll make the right guess. So there's no guarantee that the method will ever yield a solution to the non-homogeneous problem that we're trying to solve. Variation of parameters, on the other hand, is deterministic. It's kind of a crank and grind procedure where you plug in the differential equation, it will output the particular solution that you seek. The problem is that it involves a little more work, so sometimes the method of guessing, or the method of undetermined coefficients, will yield a particular solution more quickly. But if you're unable to find the solution using the method of undetermined coefficients, you can always resort to the method of variation of parameters. The method works like this. We know that the homogeneous solution will be of the form c1y1 plus c2y2 for some linearly independent functions y1 and y2 and some constants c1 and c2. As we saw with the method of reduction of order, sometimes it's useful to turn your constants c1 and c2 into functions. We'll call them v1 and v2. In this case, we're going to constrain ourselves to differential equations of the form y double prime plus by prime plus cy equals f of x. Note that I've divided out the coefficient a. We're going to assume that the coefficient a is non-zero, so you may as well divide it out. In all cases, if it truly is a second-order equation with constant coefficients, you can divide that leading coefficient off and reduce it to 1. With the hypothesized solution of the form v1 y1 plus v2 y2, note that we're replacing the one function, yp, with two functions, v1 and v2. Yp should be determined by the differential equation, one constraint. So we're going to have two functions being subject to only one constraint. We should be able to impose an additional constraint as we go along. That constraint can be virtually anything that we choose, as you'll see. Now, by the product rule, the derivative of this particular solution will be v1 prime y1 plus v2 prime y2 plus v1 y1 prime plus v2 y2 prime. Now, we're going to assume an additional constraint right now because this already looks like it's getting out of hand. We need to calculate one more derivative, and with all of these terms, this is going to be crazy. Since we can impose another differential constraint on v1 and v2, I'm going to assume that these two terms add up to 0. I don't have to assume that. I could assume they add up to some other function if I wish. It's just simple if I write v1 y1 plus v1 prime y1 plus v2 prime y2 equals 0. If that's the case, then this will go away, and yp double prime will be v1 prime y1 prime plus v2 prime y2 prime plus v1 y1 double prime plus v2 y2 double prime. Keep in mind that y1 and y2 solve the corresponding homogeneous equation. Plugging all of this into the original differential equation, we have v1 prime y1 prime plus v2 prime y2 prime plus v1 y1 double prime plus v2 y2 double prime plus b v1 y1 prime plus v2 y2 prime plus c v1 y1 plus v2 y2. All of that must be equal to f of x. Now, look at these terms involving v1. And keep in mind that y1 and y2 solve the corresponding homogeneous equation. It follows then that these three terms can be combined, the v1 factored out, and then all the expressions involving y1 will add up to 0. These three terms must add up to 0. They'll go away together first. Similarly, if we look at the terms involving v2, those terms too must add up to 0. Those terms all go away second. It follows then that v1 y1 prime plus v1 prime y1 prime plus v2 prime y2 prime equals f of x. Note, however, that we've already assumed that v1 prime y1 plus v2 prime y2 equals 0. This yields two equations in the two unknowns, v1 and v2. We can solve for them. In fact, this is a linear system of equations in v1 prime, v2 prime. And we can solve for them just as you solve any linear system of equations. You know a large number of methods for solving systems of equations of this form. Method of, say, elimination or substitution, Gauss-Jordan elimination or Gaussian elimination with backward substitution, the inverse matrix method. You know a lot of ways of solving this. I suggest that we solve this using a method called Kramers Rule. Now, if you don't remember Kramers Rule, and my students normally need a refresher, here's how it works. If you have ax plus by equals e, cx plus dy equals f, Kramers Rule says that the solution is x equals, the denominator is the determinant of the coefficient matrix, and the numerator is the same determinant but with the x coefficients replaced by the right-hand sides. This is an e. Also, y has the same determinant, but in the numerator it is the y coefficients that are replaced by the right-hand sides. Let's see this in action. Consider the linear system of equations x plus 2y equals 3, say 4x plus 5y equals 6. According to Kramers Rule, the solution for x has a denominator 1, 4, 2, 5 like this, the numerator 3, 6, 2, 5. This gives you 15 minus 12 over 5 minus 8. 15 minus 12 is 3, 5 minus 8 is negative 3. And so x is negative 1. Y has the same denominator as before. The only thing that changes is the determinant in the numerator is 1, 3, 4, 6. That's 6 minus 12 over negative 3. And so here we get 6 minus 12 is negative 6 over negative 3, and hence y is 2. You can see that this works. The solution is negative 1, 2, because when you plug it in, negative 1 plus 2 times 2 is 4, 4 minus 1 is 3. If I plug in negative 1 here, I'll get a negative 4. 5 times 2 is 10. 10 minus 4 is 6. And so this is, in fact, the solution to this system of equations. Kramers' method is really good if you have only two equations and really bad under most other circumstances. The reason being that the total number of additions, subtractions, multiplications, and divisions required to arrive at the solution increases very rapidly as the number of equations and unknowns increases. In this case, we have an ideal situation where we can apply Kramers' rule. And so by Kramers' rule, f1 prime, let's see, the determinant here is y1, y2, y1 prime, y2 prime. Check it out. Do you recognize that? That's the Wronskian. In the numerator, we're going to have 0, f, y2, y2 prime. And so you'll get minus y2f divided by the Wronskian. Similarly, v2 prime has the same denominator as before. The only thing that changes is the numerator. You'll have y1 prime, 0f. This gives y1f divided by the Wronskian. It follows immediately that v1 is the integral of minus y2f over the Wronskian dx, whereas v2 is the integral of y1f over the Wronskian dx. Make special note that on v1 you use minus y2, and on v2 it's positive y1. I want you to memorize these formulas. It is from these, remember, that you calculate, that you construct the particular solution, yp. From these two formulas, you construct the particular solution, v1 y1 plus v2 y2, where y1 and y2 form a fundamental set of solutions to the corresponding homogeneous equation. As an example, let's consider y double prime plus y equals secant of x. In step 1, as per usual, we start with an attempt to solve the corresponding homogeneous equation. You can see that the characteristic equation is lambda squared plus 1 equals 0, which has solutions lambda equals plus or minus the imaginary unit I. We get the homogeneous solution is c1 cosine of x plus c2 sine of x, since alpha is 0 and beta is 1. The Wronskian is cosine of x sine of x minus sine of x cosine of x, and that's cosine squared minus negative sine squared gives us cosine squared plus sine squared, and by the Pythagorean identity that's equal to 1. It follows then that v1 is minus the integral of y2 f. F is secant of x divided by the Wronskian. And v2 is plus the integral of y1 times f divided by 1. v2 is particularly simple. Secant is 1 over cosine, and so the integrand reduces to just 1. It follows then that v2 is simply x. Note that for these coefficients, v1 and v2, we're going to ignore the plus c's. Those will only contribute to the homogeneous solutions. For v1, on the other hand, we have minus the integral of sine x, and I'm going to convert secant into 1 over cosine. Notice that the derivative of cosine x is minus sine x. This is in the form f prime over f. It follows immediately that we get the natural log of the absolute value of cosine of x, where the plus c we ignore. The particular solution then is natural log absolute value of cosine of x times cosine of x plus x sine of x. Now I ask you, would you have made anything close to a guess of this form in terms of the method of undetermined coefficients? It seems to me there's no way you would have come up with anything even close to something like this. There's no way we can use the method of undetermined coefficients to solve this problem. We arrive at the general solution by adding to the particular solution the general homogeneous solution. As another example, let's suppose we have y double prime plus 9y equals the tangent of 3x. In solving the corresponding homogeneous equation, we begin with the characteristic equation, lambda squared plus 9 equals 0. This has solutions plus or minus 3i, where alpha is 0 and beta is 3. It follows then that the homogeneous solution is c1 cosine of 3x plus c2 sine of 3x. The Wronskian is calculated as the cosine of 3x sine of 3x minus 3 sine of 3x positive 3 cosine of 3x. You can see that we get 3 cosine squared minus negative 3 is 3 cosine squared plus sine squared, or just 3. Remember that v1 is the integral of minus y2f divided by the Wronskian. In this case, that's minus the integral. y2 was the sine of 3x. F was the tangent of 3x. And that's all over the Wronskian, which is 3. We can rewrite this as minus 1/3 the integral of sine squared of 3x divided by the cosine of 3x. To integrate this, we need to use the Pythagorean identity for the numerator to convert that into 1 minus cosine squared of 3x which we may write as minus 1/3 the integral. 1 over cosine is secant, and then cosine squared over cosine is just cosine. Let's do a u substitution. If u is 3x, then du is 3 dx. We don't happen to have a 3 lying around, so I'm going to divide that 3 off. And we'll have an additional factor of 1/3 when we integrate. We'll have minus 1/9 the integral of secant of u minus cosine of u du. You'll remember the garbage can calculation on the first term gave us the log of the absolute value of secant of u plus tangent of u, and then for the, I guess we'll distribute the negative 1/9, we'll get a positive 1/9 sine of u, and remember we do not write plus c on these integrals. Substituting u equals 3x, we get minus 1/9 log of the absolute value of secant of 3x plus tangent of 3x plus 1/9 sine of 3x. To calculate v2, that's the integral of y1 times f divided by the Wronskian, where if we multiply cosine times tangent, since tangent is sine over cosine, we'll have 1/3 the integral of the sine of 3x dx. The integral here is minus 1/9 cosine of 3x, and we don't write the plus c. We now express the solution, the particular solution, which you'll recall was v1y1 plus v2y2. v1 was minus 1/9 log of the absolute value of the secant of 3x plus the tangent of 3x plus 1/9 the sine of 3x, all times y1, which was the cosine of 3x. For v2, we had minus 1/9 cosine of 3x, and that gets multiplied by y2, which is the sine of 3x. You can see that this term will exactly cancel this term after we distribute. We end up with a particular solution like this, and hence the general solution just adds the corresponding homogeneous solution. I'd like to talk a little bit about resonance. Resonance occurs when you have an external forcing function that has a frequency that matches the natural frequency of an oscillator. So, as an example, I would like to look at a natural oscillator with no resistance. We'll do a simple case. And we'll have the external forcing function be a sinusoidal function with amplitude A. And we'll have an adjustable period. The period is 2 pi divided by omega. And so we'll be able to adjust that to match the natural frequency of the oscillator as necessary. So this is a second-order linear constant coefficient non-homogeneous ordinary differential equation. We know how to solve these. First, we solve the corresponding homogeneous equation. To do that, we look at the characteristic equation, which has solution lambda equals plus or minus I times the square root. We move the k over and divide the m. We'll have the square root of k over m. This gives the homogeneous solution as C1 cosine root k over mt plus C2 sine root k over mt. So you can see that without the forcing function, we get these natural oscillations that go on and on. Now, what happens when we throw in this forcing function? To determine that, we need to look at either using the method of undetermined coefficients or variation of parameters in order to solve this non-homogeneous part. Okay, so we have the homogeneous solution and as long as omega is not root k over m, as long as the frequency of the external forcing function does not match the frequency of natural oscillations within this oscillator, then we might suspect a particular solution has the following form. It could be, say, B1 cosine omega t plus B2 sine omega t. Now, resonance is not supposed to occur when the natural frequency does not match the frequency of the forced oscillations, but we'll solve this case just for completeness. We're assuming that the particular solution has the form B1 cosine omega t plus B2 sine omega t. If that's the case, we can easily do these two derivatives. The second order derivative of cosine is negative cosine. We just have to use the chain rule twice. We're going to get negative omega squared times this original solution. So plugging this fact into the differential equation, we get m times negative omega squared yp plus k times yp. All of that is supposed to be equal to a cosine omega t. So on the next line, keeping in mind that this is what yp is, we'll have k minus m omega squared b1 cosine omega t plus k minus m omega squared b2 sine omega t still equal to a cosine omega t. Since there are no sines on this side, but we have a sine on this side, we deduce that b2 is 0. Also, we deduce that b1 is a divided by k minus m omega squared. It follows then that the particular solution in this case is A over k minus m omega squared cosine omega t. Notice that the closer this denominator is to 0, the larger the amplitudes of these oscillations are. In other words, the closer the frequency of the external forcing function is to the natural frequency of the oscillator, the larger those amplitudes are. This makes us wonder, what happens if this denominator is exactly 0? Clearly, this will not be a solution because it's not defined. So what does happen in the case of matching of the frequency of the external forcing function and the natural frequency of the oscillator? So, if omega is the square root of k over m, then we don't expect the particular solution to have the form we had before, because in that case, both terms will be elements of the homogeneous solution. In order to get something linearly independent, we have to multiply by t. So we suspect that the particular solution will have this form, b1t cosine, and omega will be root k over m. I'll just write it as omega. b2t sine omega t. Now it's a little more complicated calculating those derivatives because we need to use the product rule. So we'll get b1, and can I just write this as c for cosine, then minus b1 omega t times sine. That takes care of the derivative of the first term. And for the second term, we get b2 sine followed by plus b2 omega t cosine. Now for the second order derivative. Here we'll get negative b1 omega sine from this term. The omega comes from the chain rule when calculating the derivative of cosine omega t. On this next term, we'll get another one of those when we take the derivative of the first part. So we're going to get two of these. And when we take the derivative of sine, we'll get minus b1 omega squared t cosine, another factor of omega from the chain rule. Over here, we'll get plus b2 omega cosine, but we'll get one more of those when we take the derivative over here. When we take the derivative of the cosine, we get minus b2 omega squared t sine. Okay, we're ready to plug everything into the differential equation and determine b1 and b2. So here we go. We'll have m times the second order derivative, that's negative 2 b1 omega sine, minus b1 omega squared t cosine, plus 2 b2 omega cosine minus b2 omega squared t sine, plus k times yp, which was b1 t cosine, plus b2 t sine. All of this must be a times cosine. In collecting these like terms, we need to keep in mind that k minus m omega squared is specifically assumed to be 0 in this case. So if we, for instance, note that here on this b1t cosine term, we have a factor of k. On the corresponding term up here, we'll have m times omega squared. So this term will exactly cancel with this term because of this identity here. Similarly, if we look at this term and this term, those two terms also cancel for exactly the same reason. So we're left with sines and cosines only. The coefficient of sine on the right is 0, which means B1 is 0. However, we get 2m b2 omega, but that's the coefficient of cosine on the left. That must be equal to a, the coefficient of cosine on the right. We deduce then b2 is a divided by 2m omega. Omega, we said, was the square root of k over m, so this is a divided by 2, m times the square root of k over m, which is a divided by 2 square root m k. That gives us the particular solution, a over 2 root mk times this t times the sine of root k over mt. There's your particular solution. So I want you to see something about this particular solution. The amplitude grows linearly. It doesn't grow quadratically or exponentially, it grows linearly. We'll have solutions that do this. So when you're behind that swing, pushing at the natural frequency of the swing, the amplitude of the oscillation should increase linearly, as long as there's no resistance. You may have seen a Mythbusters episode where they tried to attach a little device to pound against the edge of a bridge, trying to tune it to the natural frequency of the bridge to see if they could make it fall down. There is an example from the Napoleonic, well, from 1850, Angers Bridge, where a group of soldiers marching across the bridge were marching at a tempo that matched the natural frequency of the bridge and caused the bridge to collapse. This killed over 200 soldiers. So as a consequence, whenever soldiers march across a bridge now, they're ordered to break cadence so as not to cause a bridge collapse due to this exact source. If an opera singer holds a wine glass in her hand and tries to tune her voice to the natural frequency of that glass, she can force that glass to such a point that the oscillations increase and the glass can break. This is resonance. You do not want to have this designed into your electrical circuits, at least most electrical circuits, because it's going to cause them to fry. So this is something engineers should be aware of